Okay, I hope this is visible.
Yes, Peter.
Okay, great.
Very good.
So first thing I'd like to say is, you know, if you're interested in this, take a look at the OpenPower Foundation website. It's free for associate and academic members, and there's quite a bit going on there. So I hope that maybe during this course you will develop a taste for this kind of activity and become actively involved. I took a snapshot of the different working groups that form the core of this foundation. So that gives you an idea of what is going on there. So I will talk a fair amount about the OpenPower ISA, and then give you a little bit of an overview of some of the cores, some of the open cores, and I'll also talk a little bit about Power 10, which is the most recent Power ISA processor that IBM has produced. As Denison said, the slides will be available to you, and I've included references in there to where you can listen to these, listen or look at these presentations in more detail, because I'll be covering a fair amount of material in a fairly short time. So the history of power actually goes back to the early 70s. So this particular slide starts around 1985, but actually power architecture had its roots in a telephone switch project at IBM, where you know, there was a requirement to automate a telephone switch, and in order to do that, it was felt that a new and more efficient computer architecture was needed. So that telephone switch actually, you know, was designed but never came to pass. That project was cancelled. But IBM research realized that the idea of having an architecture where every instruction would be able to execute in a fairly short amount of time and would be relatively simple and operate on registers rather than directly on memory, was an idea that would be of broad usefulness to general purpose computing. So IBM research kept the project alive for more than a decade. And in 1985, there was a project launched called Project America that then eventually led to the first what was called RS-6000 system developed in Austin, Texas, which is where I am and where still, even today, the majority of IBM's power architecture development is done, even though, you know, we have many sites worldwide, including you know, several of my colleagues in Bangalore in India. So from the first implementation of power architecture with the Power 1, which, by the way, was I believe 10 chips, you know, and then a subsequent version integrated it into a single chip. There was the collaboration with Motorola and Apple to create the PowerPC processors. There's a family of embedded processors that had their own twist on the architecture. And then eventually everything sort of reconverged again into the power architecture, you know, 64-bit power architecture, pretty much as we have it today. And then a couple of years ago, we took the initiative to bring the architecture under an open governance model. So that has been done, based on a version based off of the 3.0 architecture, and continues now with the 3.1 ISA, which is the foundation for the instruction architecture as it was used by IBM in Power 10. So to give you a little bit of an idea of how this instruction set architecture is layered, so we try to make it quite easy to build a small compliant processor. So you only need to implement about 129 instructions, or actually exactly 129 instructions, to have a scalar fixed subset, which is the simplest version of that can be Power Architecture compliant. From there you can add the floating point instructions to get what was called the scalar fixed point and floating point subset, which is 214 instructions, and then add yet another slew of instructions to get the Linux subset, which is what you would need to have everything that the Linux operating system might rely on. And then there are still larger sets of instructions that would get it up to the level that we use, for example, in our AIX operating system enabled systems. And then if you add all the different features that are optional, it goes all the way up to 1419 instructions to get a full implementation of the instruction set architecture. So you can build processors from very simple to very complex. So here I'm not going to go in any detail through the different levels, but this here gives you some idea of what is included in these different levels of the architecture. So when you go to the I think the scalar fixed point subset and floating point subset are kind of obvious. They include what you would expect. When you get to the Linux subset, of course, there is quite a bit of things included that are needed to do an operating system. Things that have to do with translation support. The little endian mode is something that is required to be supported in the Linux subset, because our main Linux distribution is actually little endian these days. Support for logical partitioning, which is our architecture to create hardware virtual machines. And then going up to the AIX subset, you see a number of additional things that are kind of specific to things that are used in the AIX enabled systems. Some instructions like decimal floating point, which banks like to use. Particular versions of translation look-aside buffer invalidate instructions that are used in the operating system, as well as big endian support is something that's required there, because our AIX operating system is big endian. And then there are also a number of always optional features. One of the latest ones that we introduced here was the matrix math assist, which I'll on Power 10, which I'll talk about a little bit later. But it is an optional addition to the architecture, so an implementation can always leave it out. And then one of the balancing acts with instruction architectures and open instruction architectures is that on the one hand you want to create the opportunity for innovation, right, and allow people to do a certain amount of modification, but at the same time, of course, an architecture is only meaningful to the extent that that there's commonality across implementations of the architecture. So almost by definition, if you don't have that, then you don't really have an architecture. So within the instruction set, there is some area called 22 carved out, where people can define their own instructions, as well as some registers or bits in certain registers that can be used by these customized extensions to the architecture. Now, of course, whenever you do a customized extension of the architecture, the common tools are not going to be supporting this, right? So there's always, if you have something that is introduced as a customization that might have broader use, it is very much encouraged to bring it into the architecture maintenance process and try to bring it in as a regular part of the architecture, so that our compilers and other tools can provide support for those features that then have become a normal part of the architecture. So I'm going to talk a little bit about Power 10. So Power 10 is not an example of an open core, at least not in the foreseeable future. But it gives you an idea of kind of the range. So I'm going to talk about a very small core implementation of the Power instruction architecture, and this is kind of the other extreme, a full implementation of the Power architecture. So this is a relatively large chip, 600 square millimeters, in a modern 7-nanometer technologies, a lot of different layers of metal, 18 layers of metal, which is a very large number, up to, on a single chip, up to 15 cores with 8 threads each, and you can also think of these cores as 2 cores of 4 threads each. And that is a substantial number of hardware threads on a single piece of silicon, right? So, with 15 times 8 threads is 100, 120 threads in a single piece of silicon. And if you compare it to other architectures which maybe have 1 or 2 threads per core, typically, you would find you find implementations with around 60 cores per socket, but those are multi-chip implementations, not single chip implementation. Also, a substantial amount of L3 cache on the chip. So I'll talk about the various interfaces a bit on a subsequent slide, so I'll skip over it here. I mentioned a little earlier on that in Power 10 we put some effort into instruction set extensions and also implementation to make the implementation of AI algorithms on power processors more efficient. And we actually also put out quite a few open source libraries that leverage these these new matrix instructions, support for things like Eigen, OpenBLAS, MLAS, you know, used in AI frameworks that you might have heard of, like, you know, TensorFlow, PyTorch, ONNX, etc. Right. So this was a big push in the last implementation, the most recent implementation of the architecture. You know, I know here we're talking primarily about instruction set architecture and the cores, but you know, I can't help but I guess brag a little bit about you know, the power systems at a system level. There's a lot of innovation there too. You know, in power we have introduced innovation in memory architecture with a very high bandwidth and high capacity kind of DRAM. Basically gives you the best of both worlds of the bandwidths that you would find typically in HBM kind of implementations, and a capacity that exceeds that of systems based on regular DRAM, with the OpenCAPI memory interface. And by the way, there is another open consortium, OpenCAPI.org, that governs the OpenCAPI interface. And you know, an aggregate of about a terabyte per second of capability on the chip for memory bandwidth, and another terabyte per second of bandwidth into a highly configurable set of interfaces that can be used as an SMP interconnect, as an OpenCAPI, which is used to allow accelerators full access to the memory in the system, the same way that a processor would have. And a new capability that was introduced on Power 10 called Memory Inception, which is a disaggregated memory approach, which is a capability that the chip has, but not one that we've enabled in the first set of systems that we announced. And here's an example of you know, a system, a big SMP systems. And again, I won't go through the detail, but this is, you know, 16 sockets of that chip that I showed before, up to 64 terabytes of memory, and this is used to run some of the largest databases in the world in the, you know, in the most reliable manner. So now from, you know, the very large, I will look at the very small. So you know, if something like a Power 10 system may seem kind of daunting and difficult to get involved in, actually, you know, the entry point for power architecture, power ISA, is very, very accessible, and I think you will interact with this more later on in the course. So to my knowledge, the smallest implementation of this integer 129 instruction subset is called Microwatt. It's an open source project started by Anton Blanchard, who is one of our operating system experts, actually not a hardware designer, but he put the initial version of the VHDL that makes up this processor together with working with some of his colleagues, and it's you know fully open source implementation of a small power ISA processor, and probably you know, somewhat similar to the early implementations of the Power ISA. So this is you know, maybe just a little bit more complex than what you might find in your typical architecture introduction book. You know, I think you know, maybe there's a cycle or two more in this, but it's basically a fairly standard pipeline, you know, implementation of the architecture, and then also around the core there are some other things, you know, like Ethernet, DRAM, and UART IP that would help you build a small SoC based on this architecture. So actually they and this slide is a little bit out of date. I think it may have grown in size again a bit since then, but it really is quite small. If you're not familiar with FPGAs, a lot is a lookup table, right? FPGAs are built from little wire routing elements and little logic tables, and by programming these logic tables and routing elements, you can create hardware designs in reconfigurable hardware, and you know, something in the order of 10,000 of these lookup tables is really not very big at all. So you can implement this on an FPGA of very modest size. It's still you know, quite an active project. So I took a snapshot a little earlier today, and you know, you see that even here, you know, in the last week, there are regular contributions being made, and you see some of the names of the most regular contributors here. So this is I think it's a very nice project. I hope you will enjoy learning more about it in this course, and you know, again, a very accessible way to get into the architecture and learn more about computer architecture and microarchitecture. This is quite doable. So I'll spend a little bit of time next on some of the other cores that have been contributed. So this is the A2 processor family, and there are 2 processor cores that have been contributed to open source. A2I, which you know is an in-order design, which has 4 threads per core, and was used in the Blue Gene Q supercomputer. Well, you'll hear some of the details, and then A2O, which is an out of order core with you know more performance per thread, and that is but fewer threads, actually 2 threads per core. And as you will see, both of these also can be realized on FPGAs, but those FPGAs would have to be a bit bigger. So you know, this is a family of modular and flexible processor cores, and intended to be building blocks for SoCs. So to give you an idea of how big and fast they are, so the A2I core, when realized in 45 nanometer, which is where I think we built it for the Blue Gene processors, was a 3 square millimeter core. It ran all the way up to 3 gigahertz. And if you would take that core to a modern technology, it'd be just a few tenths of square millimeters, so really quite small. 16 kilobyte IND caches, as I mentioned before, this is a 4-way threaded processor, dual issue. Okay, I think I will skip over the other details. So here is an example of a communications processor actually realized with the A2I, with the A2I cores. So this chip was manufactured and tested and everything, it eventually it was done in a partnership. Eventually, it didn't make it to market, but this was actually mostly because of sort of where businesses decided to focus. But it's it was a fully working design, and I think a good example of a compelling SoC that could be realized with these cores. So it was, as you see today in chips, also from companies like Apple and so on, right? More and more, processor cores don't necessarily make up even the majority of the area of these chips, right? All kinds of accelerator IP tends to play a larger and larger role in these SoCs, and you can already see that here. This is a quick overview of the microarchitecture. Again, I won't go into much detail here. If you want to learn more about it, listen to this talk by Bill Flynn during one of the OpenPower summits. I think both the talk and the full set of slides are available, and I have a link later in the presentation. This particular implementation is not fully compliant to the last version of the architecture. So a little bit of work would have to be done to take this core and turn it into something that is compliant to one of the subsets of the architecture. But it's not terribly far away from that, because it is not that long ago that this core was done. As I mentioned, the core can be implemented on an FPGA. So in this particular case, it's a Vertex Ultra Scale FPGA from Xilinx, where it was realized, and this project is also available. If you go to github.com OpenPower cores, A2I is where you can find this design. I won't go through this in detail. This slide, gives you a little bit of the details of what would need to be added, to make it compliant to the open version of the architecture. And here are some activities that you could engage on in the community, based on this core. And then I'll also, before I take some questions, I'll briefly mention the A2O processor core. So A2I is and also Microwatt are written in VHDL. A2O is written in Verilog. So those of you that may be more familiar with Verilog rather than VHDL might like to look at A2O. in terms of the level of the architecture, is very similar to A2I. So also with A2O, there's a little bit of work that would need to be done to bring it into compliance with the 3.1 version of the architecture. As I mentioned, this is a two-threaded architecture. This one is out of order, and it's a little bit bigger in general. This is 32 kilobyte caches. I think the address translation is maybe similar in size, and it supports both big and little endian, which is important because our Linux operating systems these days are with PowerPC 64 LE are little endian focused. Here's a block diagram of that processor. Again, I won't go into detail here. I think the previous one was something like 0.017. You can see that this one would be, not quite twice as big, but a little bit bigger than an A2I core. Okay, and also this one can be implemented in an FPGA. I do believe that you have to subset the design a little bit to get it to fit in an FPGA. But you can realize a fully functioning version of this core in an FPGA as well. And as I mentioned, to bring it into compliance with the architecture, some similar changes would need to be made as with the other one. And actually, the work in here to realize that the FPGA implementation was done by a number of interns at IBM during the summer. Right, so a project like that can be done in a reasonable amount of time. Okay, and then I guess the last thing, and the slides will be available. I included a number of references, so you know where to find these things. So with that, I guess I'll end my presentation, and I'd be happy to try and answer some questions.
Thank you, Peter. Thank you for the wonderful presentation, as well as a lot of pointers to the students and faculties here. Thank you very much. Participants, any questions for Peter, and also the panelists? Any questions for Peter?